Okay, the intro is over and I'm back. All right. I'm going to pull up, it is 11:59. I am going to pull up the I hope I'm not making this sound like I want to get the quiz up. I know everybody took the quiz. Grab your Menti codes, please. Don't forget to grab your Menti codes for sign in. You got another minute. I'm going once that's gone, it's gone. All right, day 2. How many people do we have responding on day 2? Oh, I got a poor show out on this. Oh wait, no. What am I talking about? See, this is I just changed 186. Great. I just changed my monitors. I ordered 2 new monitors. I hope they get approved. I just saw an email said they need more info from me. I hope it's not a checkbook. Are there any advantages of using WebEx via YouTube or vice versa? Gabe, I don't think so. Everybody on YouTube says they like that, and they still are able to get the PDH because they're signing in. And what you should be seeing right now is the 432218 code, and it is 12 o'clock. And yeah, YouTube may be blocked by some people. That's true. I've heard that. I know in our organization we've had that issue when we were behind the firewall, and it is a couple minutes behind WebEx. Thanks, Nihan. The chat is faster on WebEx than on YouTube. That's true. You're probably right there. But hopefully I don't miss anybody. Okay, well, it is 12:01 and we are going to get this show on the road. And what I got to do. All right. Well, I got enough answers here. I'm going to show the codes when I get up here. So let's do the intro stuff first. All right. So welcome to the continuation of NEC 2020. We're talking 2020 code changes, National Electrical Code. Yesterday we got through Article 90. We got through some things in 110. We got the service entrance requirements behind us, I believe. So that's all good stuff. You just hide some chats here and cue this. Whoop. Didn't mean to do that to you guys. I got to do Q3, I think. Yep. There we go. That way you get me out of the picture. So yesterday was service entrance equipment and all the changes that happened there. I think that was a pretty good discussion. We had some good feedback. Please keep commenting. That is, I think, an important part of the program. Everybody out there has probably a lot more information than I do, and because of that, I muted everybody. So the WebEx people, I have to mute you because otherwise it would just not be bearable. And so you're all muted. Please use the chat box, and it looks like everybody is using that. That dialogue down there is, we have somebody who's in prison. Sorry about that. That's a good thing, I think. Just kidding. So all of your microphones are muted. Please use that chat box. And I think I introduced myself yesterday, and again, I'm just going to restate the fact that everything that you hear is my opinion alone. I do not speak on behalf of my fellow Codemaking Panel 2 or Codemaking Panel 10 members, nor NFPA. These are some of the committees that I sit on. I'm engaged with various organizations as well. My background is power engineering. I hear somebody wants to talk again. But my background is power systems engineering, and I've been with Eaton since 1995, which is a long time. These are, again, 3 organizations that I belong to: the International Association of Electrical Inspectors, NFPA. The IAEI, I can't say, I can't tell you guys how important I think that organization is for networking and understanding the code and going to events locally in your areas. Look up the IAEI, find the chapter or division that's in your area, get involved, go to the meetings and learn something. I think you'll be impressed, and maybe sometimes you can share your knowledge. So very good organization. All right, so this is where we were yesterday. We went through global, we got into service entrance changes, and actually, I believe in service entrance, I got to go down through here. Well, let me just pick it. Yeah, I have this slide sorter. There we go. See how easy that was? So we did not do these two things down in the bottom right. But before I get to that, the quiz. I know everybody out there is worried about how did we do on the quiz. Well, here we go. These were the questions. Which incident energy? I think that's the first question. Let me make sure I didn't. No, that's not the first question. Here we go. First question. Higher fault currents will always drive higher incident energy values. 114 of you are star pupils. 72, 115. Look at that. I love that. You put that up, people see the code, they get in there and they start putting, and they're like, I'm a star pupil, I'm a star pupil. I know what the answer is. But in any case, the reason I say higher fault currents do not always provide and produce higher incident energy is because when you increase your fault currents, you're going to be moving into faster clearing times of the overcurrent protective device. We're going to be talking about 240-67 and 240-87, which is all about arc energy reduction. And there are two fundamental principles you have to understand with regard to the overcurrent devices, because overcurrent devices are going to be those things that reduce your incident energy. And it's higher currents that will get you faster clearing times. Now, if you are in, say, the instantaneous region of a circuit breaker and your clearing time is constant, yes, a higher fault current will give you a slightly higher arcing current, which will get you at the same clearing time. The higher current will get you a higher incident energy. But the change is going to be only in regard to the amount of current because your time is constant. When in some cases, in which we'll show you, when you lower your fault currents, you can be in much longer clearing times on the overcurrent device, and that will generate a lot of incident energy. So I've heard people say, all I need to do is lower the fault current, and I'm going to lower my incident energy. And when they did that, they realized when they did the calculation that the actual energy went up, and they couldn't understand that. And we're going to learn and understand that today together. So for those 76 and the 7 that are on the phone, you're going to understand how important it is to understand fault current and understand the clearing time of the overcurrent protective device that's supplying, feeding power to that distribution equipment. Okay, which incident energy reduction technology is the fastest? ZSI, arc reduction maintenance switch, differential relaying, and I'm not sure. So here's the thing. Anytime you put a brain into the picture, I don't care if it's electronic brain or if it's your brain, when you got to think about something, you're adding time. And I always relate this to when I used to go hunting. When I first started hunting with my dad, I carried a semi-automatic shotgun. And when I would pull my gun up, shoot at a bird, and I would put my gun down, and my dad would look at me and say, put your safety on. And I'd look down and my safety wasn't on, I'd put it on. And then the next bird would come up, I'd pull my gun up and my safety would be on. I couldn't pull the trigger, I had to turn the safety off, and it would take me a long period of time because I had to think about what I was doing. The moment it became an instinct, the moment that I did it so often that I would go through that entire process and I would turn that safety off, turn that safety back on again, and it would just be instinct. My brain wasn't as engaged and it was much faster of a response. The same thing with an overcurrent protective device. The arc reduction maintenance switch is an analog circuit. There's no brain in the picture. There's no microprocessor. When you get into zone selective interlocking or differential relaying or any of those, most of those other technologies outside of the arc quencher, which we will talk about, when you get into most of these technologies that have a brain, that brain has to A, detect the current is flowing, B, compare that with a set point, make sure it's above the set point, C, possibly in zone selective interlocking, check for a downstream signal, and then if it's there, make a decision, and then trip. And that process on ZSI, zone selective interlocking, could take up to 0.07 seconds. The arc reduction maintenance switch is faster than instantaneous, so it's faster than 2 cycles. And remember, 1 cycle is 0.0166 whatever seconds. So the arc reduction maintenance switch is the fastest solution on there, and you just have to, and that's why it's important to be in the class on Thursday to understand how overcurrent protective devices work, because that will help you completely have the fundamentals to understand why some technologies react faster than others. All right. So our arc reduction maintenance switch was the right answer on that one. How about all fuses 1200 amps and above will now require an arc reduction technology installed because of 24067. We have an overwhelming 138. See, now they're piling on. People are logging on to Menti. They're seeing that big black bar there that's 140 people, and they're jumping on that bandwagon. And I'm telling you right now, you're jumping on the wrong bandwagon, because you should be jumping on the 43 false bandwagon, because that is not a true statement. And we're going to review 24067, and I'm going to help you understand why not all fuses 1200 amps and above will require an arc reduction technology installed because of 24067. So the 52, you get a little gold star because you have such a big discrepancy between the 152 and the 46. Throw me a bones. You need to stand up right now, jump around the room, don't hurt anybody, and don't come within 6 foot of anybody else, and enjoy your moment, because when I go to this next question, you're probably going to be crying again. So the right answer to that is false, and you will understand why when we get into this program. ZSI is designed for breakers to selectively coordinate. I love this. One of these days, this question is going to be answered correctly, and I'm going to be jumping around the room. The 123, 124 of you, that is unfortunately, you're in the wrong bucket. You should be down there in that 56 and 57 bucket. Those guys were probably in the class last week, because I went over this. And if there's anybody in that 125 bucket that was in my class last week, send me back those PDH hours, because I taught this last week when we talked about selective coordination. Zone selective interlocking does not get you selective coordination. ZSI is an arc reduction equipment protection technology. And we're going to talk about this to help you completely understand that, so that the next time you get this question, I'm going to have all 260 of you in that false bucket, and I'm going to feel great about myself. But zone selective interlocking, that's why it's a part of 24087 as an arc reduction technology. It is not, if you do not set your devices, your overcurrent protective devices, with their set points, you're not going to get selective coordination just because you have ZSI. If your fault current is higher than the instantaneous pickup of both of those devices, you're not going to get selective coordination because of ZSI. So we're going to have fun with that one as we move through it. Installing ZSI between the main circuit breaker and feeder breakers at the service entrance equipment reduces incident energy on downstream equipment. We got a lot of work today. This is why I think it's going to take 2 hours right here. These last 3 questions. ZSI, think about that first word, zone. You have a zone of protection. If anybody played football or anybody played basketball, any of these sports, you had a zone. If something happened outside of your zone, did you get blamed for it? No, because you were working a zone, and you can't take credit. You can't help things that don't enter your zone of what you're doing. And that's what zone selective interlocking is. Zone selective interlocking detects arcing and sparking. It detects when fault currents go into the zone, but don't come out of the zone of protection. So they provide protection when faults are in the zone of protection. Now, I can layer zones of protection. I can extend the protection of ZSI downstream by increasing my zones of protection, yes. But when it's in this service equipment, connecting the main with the feeder breakers or branch breakers that's in that equipment, you're only protecting the bus in that equipment, not anything downstream. Big misconception that could get our electrical workers in a bad pinch, because if you think you get protection because you have ZSI on the main equipment and it works downstream, you could dress inappropriately. So we're going to talk about that, and you will hopefully completely understand ZSI before we get out of here. The first level of defense to avoid an arc flash injury is working de-energized, establishing an electrically safe work condition, wear proper PPE, add distance between worker and energized bus. And we have one individual who we love, we cherish, who has just a big question mark, and that's why that person is dialing in. So thank you for being here. So the 134 that say work de-energized, I used to make that same mistake. I used to say, turn it off before you work. And I would have a good friends, my friends who were involved with 70E and other in the safety world would tell me and correct me. And, when you're in the codes and standards world, correction comes harshly, have a thick skin. And they'll remind me that you are not turning it off. You are establishing an electrically safe work condition. And a part of establishing an electrically safe work condition are a lot of other things. You have to understand all of your sources of power. You have to do a lockout tagout program. You might have to put ground straps in, temporary grounding for safety. So establishing it's not enough to say work de-energized. You have to make sure that you follow the 70E guides of establishing an electrically safe work condition, which is a lot more than just working de-energized. And we're going to bring that up. And the reason I put that in there is because on some of these technologies, there's lockout tagout opportunities that we should be providing to the electrical worker. So I'm going to be sharing some of that with you. That's why it's important to establish an electrically safe work condition. Which of the following do not impact arcing current calculations? Ooh, now if you're not a 1584 guru, I would not expect you to understand this. So let's think about it. We know voltage does. I mean, if I have a 480 volt system, think of voltage as pressure in water, right? If I have a lot of pressure pushing my current through the system, a higher voltage, I'm going to get higher arcing currents. I'm going to get more energy. Bolted fault current values, that's going to matter because I calculate arcing currents based upon the bolted fault current. So if I have less I could have so low of a bolted fault current that the arc doesn't even sustain itself. Okay, it self-extinguishes. I could have a very high bolted fault current value, which will generate very high arcing currents. We're going to talk about that. Electrode configuration, VCBB, HCB, you probably don't know what that is, but you're going to learn that today. That definitely does. That tells you which way the electrodes are configured, and I will show you how it does impact the arcing current calculations. Enclosure size does not impact. So the 109 that are in that, pick the right answer because the size of the enclosure really dictates how much energy is forced out. Think about it. Just think about it from a hose perspective. There you go, a water hose. It just popped in my head. If I take a water hose without any nozzle on it and it has a nice 1-inch opening, I'm going to get water to just flow out. What do I do if I want to push more water out, or if I want to push more force of water out of that nozzle? I start to close up that nozzle a little bit. I put my thumb over it and I'll start closing it up and I'll force more out faster. So when I have a very large enclosure, I will have that energy come out in a certain rate. But when I constrict that arc, I will cause that energy to forcefully come out and reach a further distance, etc., because I have reduced the enclosure size. But I haven't changed the electrode configuration. I haven't changed the distance between the electrodes. I haven't changed the voltage. I haven't changed the bolted fault current value. So I won't change the arcing current, but I will change the amount of force that the electrical worker faces in front of that enclosure. So the right answer to this one that doesn't impact arcing current is the enclosure size. All of those other parameters besides the I don't knows do impact arcing current. It's just an interesting fact. The upper short circuit current limit of 1584 to calculate arcing current is, there's a lot of not sures. And you know what? This one slapped me in the face It was after 24067 and 24087 came about, and I'm putting together my educational materials and trying to provide tools to our customers to apply fuses and circuit breakers. And I realized that the upper limit, IEEE 1584, out of bounds is 106,000 amps. So there is no way for me to calculate an arcing current when my available bolted fault current is greater than 106,000 amps. We're going to talk about that. And that presents a unique issue when we're meeting 24067 and 24087 when your bolted fault currents are greater than 106,000 amps. So if I'm at a secondary network, I'm downtown New York City, Abasi is sitting there in his science lab, and he's approving drawings, and he's working hard to make things safer, and he comes across he's got 180,000 amps available at this building, and the engineer gave him a set of drawings, and it says, I can't calculate arcing currents to meet the requirements of 24067 to do a comparison of the arcing current with the clearing times, nor the technologies employed, because there is no mathematical equation for me to calculate arcing current when my fault current is greater than 106,000 amps. What do? I have an idea. I have a solution. I'm going to present that today, and hopefully we're going to generate some dialogue on that specific thing. So 106,000 amps is the limit. It's not 200, and those 93 and there's others. So 36 of you out of 260, 38 of you now, now that you all know the answer, have gotten that right. So thank you, and we will learn more about that as we get into 24067. That's going to be a really good discussion. I learned a lot just making those slides and making some of the information. Line side barriers required as part of 11016B R2. Reduce the likelihood of incidental contact. Absolutely. That 200, that big red bar, I love to see it. That's what it's all about. Protecting the electrical worker from electrical shock. Gotta love our electrical workers. They put their lives on the line every time they open up a dead front. Ground fault protection of equipment can be tested by secondary current injection testing upon installation. 153 say true, 57 say false. Now, this is a 2020 code version class. I don't have my 2017 book, but guys and gals, secondary current injection testing became illegal for GFPE testing in the 17 code. You have to do primary current injection testing. That is a must. So you've got to do primary current injection testing. That was a code making panel 10 decision, and that was what influenced and why I put it there, which I thought everybody was going to get. I put that in there because that is what drove code making panel 10 to beg the question on why we don't have field testing of our arc reduction technologies when we require in 230.95 performance testing. And I'm going to read, and this language didn't change in the 20 cycle, but here's what it says in 230.95. I know everybody has their code books. I know everybody's got it right now, and they're opening to 230.95 C. It says the ground fault protection system shall be performance tested when first installed on site. This testing shall be conducted by a qualified person using a test process of primary current injection in accordance with instructions that shall be provided with the equipment. So secondary current injection testing is no longer permitted. It has to be primary current injection testing if you're on the 17 code, not the 2020 code. And most of those people on this photo are probably on the 17 code. Beautiful. All right. We are learning. We're learning. This is a good thing. And that was the quiz. I hope you enjoyed the quiz. I did. I love those things. I'm excellent streaming. I've got good streaming. I'm going to take a look at some of the questions. But when I enter that current Menti mode, it doesn't ask me for my name and email. I got to check my Menti codes. But in any case, while we think about that, let's take a look at some of these questions. I'm going to look at registration. I'm going to do the sign-in. I'm going to make the just for those who are having trouble, class attendance for 2020-04-07. Just going to save these results and make sure that that's working. While that's saving, I'm going to put that code back up again real quick. I'll say it instead of talking about it. Take a look at the class attendance. I could have swore I was seeing that stuff on there. I just want to make sure I got the right code. So if you're looking for the class attendance, the code that you're going to use is 432218. 432218. And when I downloaded the file, I am seeing names in there. So that is the code. It is taking the information. So good. Hopefully the guys on YouTube. And I do not take the score, right? And even when you sign in with your name, I'm not using I'm not giving you a percentage or anything like that for the quiz. I'm not going to base giving you a PDH certificate on your capabilities on that quiz. So just don't let that fret. Don't fret on that. Quit sweating. Okay. To our class, there will be another quiz. Thank you. So it looks like the guys on YouTube are helping each other out, which is a good thing. All right. So I'm going to look at my chat on WebEx. No voice on WebEx. You got to swap on. I got to hit that. Understand taking into consideration same time. Menti didn't ask for a code. Led right into your questionnaire. Hopefully you had the right code. I trust you'll explain injection testing. Yes, I will, Mr. Shapiro. In fact, I have a little video I'm going to try to show. Okay, Menti didn't ask for a quiz. Code. New York City, we were on the 2008 code. Oh, New York City's on the 08 code. God bless you guys. You guys are moving, though, with 2011 edits. Okay. All right, so with that, I am going to, I think, yep, I'm going to send PDHs. You'll get all the information. And thank you, Chris, for sending out the codes, 432218. All right, so let's move into our 24067 discussion. And away we go. Slideshow security. I love that. Cybersecurity. We're going to do one of these on cybersecurity in case if anybody's interested. I'm working on my cyber guys to put together a good 2-hour session on cybersecurity, and I'm working on my Kraus Heinz guys too to put a program on. So for your Haslock guys out there, 24067. 24067. Really, the idea for that began when 24087. So here's the journey that 24087 has had, and then it prompted 24067 because 24087 is on circuit breakers only. It entered the code in 2011. It's been modified ever since. You know, good code is like a good wine; it gets better with time. But somebody did remind me that if you go too long, wine can turn into vinegar. So, but the code never turns into vinegar. 2011 is when it went into the National Electrical Code, and it was continued to be refined. And it was in the 17 version of the NEC that basically they said, hold on, you know, we're doing all of this on circuit breakers for these large breakers that have a large delay. In fact, it started, the requirement in 24087 started with on circuit breakers that didn't have an instantaneous, and I call those the double wides. Those are the big boys, and we don't sell that many of those out there. But it's not just the breakers that don't have an instantaneous that present a challenge. It's also those breakers that have 30 cycle time delays, which have an instantaneous and have a short time delay, but we just have to address the arcing currents, etc. So in any case, I gotta not look at these chats. It's just driving me crazy. So 24067 entered the code as part of the 17 cycle with an effective date of January 1st, 2020. And what that did was, there was one manufacturer who had a solution, and the desire of the panel was to make sure that all manufacturers had some time to come up with solutions. So the way the language reads, it says where fuses rated 1200 amps or higher, where they're installed, so it's keyed off of the fuse. A and B apply, which we've got to modify this for my fellow panel 10 members. It should be A, B, and C. I don't believe. Let me just check my book. Just make sure that my book is right. But 24067 doesn't say A, B, and C. 24067. No, it says A and B shall apply. I believe that should be and C too. But in any case, and it still has the January 1st. So we released the 2020 code with an effective date of January 1st, 2020. So we got a little bit of cleanup to do on this requirement, but we have it separated into A, B, and C: documentation, method to reduce clearing time, and performance testing. You'll notice there were changes in all three of these. So these still get the chance to to be modified over time. So I'm going to let you in on a little secret. We have a tool that you can use, and I think I can call it up. I'm going to call it up. This is a little tool that we use to help you understand when you're applying a overcurrent protective device as a fuse, if you need to employ 24067 or not. So in true busman fashion, trying to make your lives easier, we have the FC Squared app, which is very popular, and this app should be very popular soon too. I'll show you what it does. You can basically give it works off of IEEE 1584, the 2018 version, the latest version. You have the gaps between electrodes, and I gave you what 1584 tells us. They use 25 millimeters for shallow, low voltage MCCs and panel boards, 32 for low voltage switchgear. Most of the engineers I talk to will use 25 for switchboards as well. That's why we defaulted to 25. This is the vertical bus, and we're going to talk a little bit more about this. You can configure VCBB, VCB, or HCB. So this gives you those parameters. And all of these this doesn't calculate incident energy. This will just calculate your arcing currents. And these are the only things that impact arcing currents: VCB, VCBB, and HCB. And we'll talk about that. This is the voltage. This is your available short circuit current. And then this is your fuse size that you're going to apply this on. So if I have these gaps, 480 volt system, and let's say that I have a 2500 amp fuse. Actually, that's the fault current. Let's say that I have, I don't know, 100,000 amps. 100,000 amps of fault current, and I'm going to pick a 2500 amp fuse. It's all in KA, so you see, you're learning as I am. So it's all in KA. So 100 KA, 2500 amp fuse. I calculate. We have little scientists back at the lab who do these calculations for us. And we have the maximum arcing current is 47.32, and we have a minimum arcing current. Now, you'll say, Tom, why are you calculating two values of arcing current? That doesn't make sense. The code doesn't say which of these arcing currents, so why are you calculating two? IEEE 1584 calculates two values of arcing currents. And one of the main reasons is because sometimes when the equations that we use in 1584 were developed in a lab, and we do tests over and over and over and over and over. And Dr. Lee down in Texas, he takes all that data back and he graphs them, and then he creates an equation to do curve fitting. And they calculate the minimum and maximums, because if you think about all these data points that you would have in your system. So I keep forgetting I have the ability to do this here. So if you think about if you have a curve, whoops, all right, pen. So you have a graph, right? And you have data points for different values of fault currents. and you say, well, my arcing current was here, my arcing current was here, my arcing current was here, and when I increased it, my arcing current was here, my arcing current was here, my arcing current was here, and you're doing all these great things, and you have all of these data points, and then you can draw a line on the bottom edge, and you can draw a line on the top edge. And so you know that for any bolted fault current, you're going to have an arcing current that's going to be a minimum and a maximum. So it gives you your range. And what that also helps us do is when we start to learn about the clearing times of overcurrent protected devices, we don't want to be on the knees. So if I have a circuit breaker that has a trip curve sort of like this, and this is a real ugly trip curve. If one of my data points is here and my lower one is here, my higher fault current, my higher arcing current will clear faster than my lower arcing current. So I would want to use the lower arcing current for the worst case scenario for my arcing calculation for my incident energy. So sometimes my lower arcing current will give me a higher incident energy. Now, the reason we bring all of this up is because you have to understand that the code is going to require you to compare in the worst case scenario when you're thinking about moving into either an instantaneous region on a circuit breaker or a 0.07 second mark clearing time. The lower of these fault currents is going to be your worst case. So you want to make sure, it doesn't say this in the code, but this is Tom's advice. As just from a power engineering perspective, we know that lower arcing current can give me a longer clearing time. So I want to make sure that the lower arcing current is either in my zone selective interlocking region, in the instantaneous region, or at a clearing time of 0.07 seconds or faster. So everything I talk about moving forward, I'm going to be keying off of, with regard to 24067 and 24087, I'm going to be keying off of that lower arcing current. And I think as we move along, if you don't understand it now, you will get it as we move along. So what this tool tells you is that the KRPC 2500 and the KTU 2500 amp fuses will have a clearing time of 0.07 seconds or faster, which you'll learn why that's 0.07 seconds numbers important. And you do not require an arc reduction technology. So this is just a tool, and I'm going to explain this moving forward. I wanted to make sure you had this. It's arc-qa.bussmann.com. Very important. I would bookmark this. You can, again, add to session. You can make changes up here. You can say, well, I'm going to do I'm at 208 volts. You can do 208 volts and recalculate that same number. And now that 2500 amp fuse fails. Now you need an arc reduction technology because your arcing currents are way much lower than what they were before. My minimum is only 19,000 amps at 208 volts. If I increase that to 480, and I did a recalculate, remember 19.4, calculate 41. Look at that. I take my voltage from 208 to 480, and I moved my arcing current from my minimum arcing current from 19,000 to 41,000 amps. That will get you a faster clearing time and into the current limiting region of these fuses much faster. So higher currents will get you faster clearing times. So you learned a couple lessons there. So this is a good tool. Use it, play with it. If you don't really understand what you're looking at, it's not a tool you're going to be able to use. So, but you should understand what you're looking at. Don't blindly use tools. So anyway, but that's a new tool you can play with. All right, get back to our regularly scheduled program. Talk about from an overview. We already know that it entered in the 17 code. I already talked about that. We already talked about that. Impacts fuses 1200 amps and larger. So where fuses, the way the language says, I call them trigger points. You have various trigger points to whenever you're looking at any code requirement, you've got to figure out, does it apply to me? So what this tells you is that if I have a fuse 1200 amps or higher installed, 24067 A and B are going to apply, and the requirement shall become effective January 1st, 2020. Now, there's no restrictions, whether it's AC or DC or other than dwelling units. It's all fuses 1200 amps and above. Now, I have to tell you there is one restriction. If you go to 240 dot, and this was brought to my attention last week when I think I showed this same slide. 240.1, the scope of Article 240. So this is, remember in yesterday's class, in the very beginning, we talked about articles, parts, sections, and things of that nature. 240.67 is in part, I think, 6 of 240. Yep, nope, yeah, part 6, cartridge fuses and fuse holders. So 240.67 is in part 6, which is titled cartridge fuses and fuse holders. If you look at 240.1, 240.1 tells you parts 1 through part 7. Now that means parts 1 through part 7, we're in part 6. Part 1 through part 7 of this article provides the general requirements for overcurrent protection and overcurrent protected devices not more than 1,000 volts nominal. So what I do have to add to this slide, and I'm going to make a note. Oh, can't make a red note. I'm going to say not over 1,000 volts. 240.1 is your reference. Understand when that applies. So 240.1 tells us that that is the only restriction. So no restrictions is not quite right. I do have to fix that slide. Reference 240.1, and it's only applied to up to 1,000 volts. All right. I see I'm getting subscribers on my YouTube channel. Thank you very much. I'm going to be putting more material out there, so please subscribe to my channel, and hopefully we'll learn stuff together. We just Kirk Gowdy here. We have I bet you there's not too many people who ever heard that term, Kirk Gowdy. My dad used to say that all the time. Give me a Kirk Gowdy. We're watching Steelers play, and that was a news reporter, a sports reporter back in the day, who would give the scores of points. But anyway, 314 on YouTube. God bless you. Thank you very much. This is good stuff. Okay, so the requirement is also not based on the switch nor the holder. It's the fuse size, because it says where you have a fuse, not fusible equipment, not a fusible switch, or anything like that. A fuse holder can be 1,200 amps, but if I put a 800 amp fuse in that fuse holder, I'm not fall under the requirements of 240.67 just because I have a fuse holder of 1,200 amps. It's keyed on the fuse. Okay, so 240.67 tells us that we're required to have an arc reduction technology to be employed if the fuse doesn't have a clearing time of 0.07 seconds or less at the available arcing current. So now what you see now is that you need to there's a term now, arcing current. Arcing current is not defined in the National Electrical Code. Public input, hint. There's no definition of that. So I showed you that 1584 calculates a maximum and minimum arcing current, but the code doesn't say have a less at the minimum available arcing current or maximum available arcing current. So technically, I could use the higher number and get away with it, but I'm telling you from an engineering perspective, my guidance is I'm a conservative person. When it comes to engineers, we're supposed to be conservative from a safety side. That lower arcing current is what you want to use. So what you can tell is what's going to happen is you're going to have to A, calculate the bolted fault current, B, calculate the arcing current, the minimum arcing current, and then you're going to have to take a look at the trip curves to see if it applies. And that's why the Bussmann tool is really critically important. So this is the technologies. These are the technologies that are permitted to be used when your clearing time at the arcing current is longer than 0.07 seconds. You can do differential relaying. You can do an energy reduction maintenance switch with a local status indicator and a compass in the stock. Energy reducing active arc flash mitigation system. Current limiting electronically actuated fuses. I'm going to explain what that is a little bit later. And or an approved equivalent means. Now that approved equivalent means has been in there since day one, and the reason it is there is because they don't want to stifle innovative solutions in the area of electrical safety and reducing arc flash. I may come out with a Van Ducky tomorrow that is the best Van Ducky that you've ever seen. It's a UL listed Van Ducky, and it's the fastest acting arc current clearing Van Ducky that that it defies the laws of freaking physics. Okay, and it's not in this list, but everybody, and it should be able to be approved. So that approved equivalent means we're going to cover on ways to help your AHJ, your authority having jurisdiction, approve the approved equivalent means. And these are just, again, my opinions on how I would do it. But we're going to talk a little bit about that moving forward as well. Now you need documentation. This is one of the changes that was made, and they made this change to 24067 and 24087. You have to provide documentation that demonstrates whenever you pick a arc reduction method or a technology, whenever you pick that technology, you have to show that it will operate at that arcing current. So that's an important a piece of the pie that you need to show. You just don't blindly apply an arc reduction technology. You have to show that it'll actually do something for you. And I think that's critical. I think that's important. Here's what I think is going to happen. Because we're going to be consciously thinking about arcing current at these devices, we're going to be making conscious decisions to ensure the technologies for reducing incident energy are employed and functioning. So that may change how we design a system. You may break those overcurrent devices down into smaller overcurrent devices with the same bolted fault current, and that will help those devices act faster. But you're going to be making conscious decisions on everywhere where you have a fuse or circuit breaker 1200 amps and above. So we're going to do a deep dive. All right. So not all fuses, again, not all fuses 1200 amps and above are going to have an arc reduction technology applied. And I think I explained why, because some of these arcing currents are going to clear faster than 0.07 seconds. Now let's take a look at this language. So these are all the trigger points, 1200 amps and higher installed. So that's one of the trigger points. If you have a fuse that's 1200 amps and higher, you know you got to go look at 24067. And if you calculate the arcing current and it has a clearing time longer or greater than 0.07 seconds, that is the second trigger point that's going to get you into whether or not you need an arc reduction technology. Now let's talk about this briefly. For every 1200 amps and above fuse, now we talked about time current characteristic curves on our selective coordination class last Tuesday, 1 week ago, if I'm not mistaken. Every curve, this is what I call the resume of an overcurrent protective device, because it shows you how it's going to perform whenever you put current through it. So this particular 1200 amp fuse establishes a clearing time of 0.07 seconds for any current greater than 14,400 amps. So obviously we're going to be looking at arcing currents, but as long as I drive more than 14,400 amps, I know I'm going to have a clearing time of greater than or less than 0.07 seconds. And what I'm doing there is basically I'm going to be plotting the arcing current, the lowest arcing current, if you're going to do things, in my opinion, the right way. You're going to display or plot the lowest arcing current and establish a 0.07 second clearing time. So, and I know arcing current is not a term that's in the NEC right now. It's not defined anywhere in the NEC, but it is defined in IEEE 1584, and it is calculated in IEEE 1584. And what I'm showing you here is I'm showing you the 2018 version. So we have the latest version of IEEE 1584 that we're looking at. There's all ink on slides. And they define an arcing current as a fault current flowing through an electrical arc plasma. Now, what is an arc plasma? So an arc flash event is going to take the components that are inside of that piece of equipment and vaporize them. You're going to create a cloud of vaporized material that the current is going to flow through. So when current flows through this cloud of vaporized copper and steel and plastics and all of the different things that you're going to see inside of that inside of that cloud, that I call it a plume, and I get made fun of, but I call it the plasma plume, and don't laugh, but that's what I call it. But that plasma plume is going to generate a way for the current to flow outside of the normal path through the air, because it's energized, it's full of these particles that are conductive, but it adds resistance, it adds impedance into the system. And what that impedance does is it reduces the current from, if I have 60,000 amps of bolted fault current available at this piece of equipment, when this explosion occurs and the current flows through the air, it's going to add impedance, it's going to reduce that current. When you add impedance into the system, it reduces the current. And that's what's happening. That's why your arcing currents are always going to be less than your three-phase bolted fault current. Okay? Now, 1584 gives us the equations to calculate both of those values of arcing current, but it's important to understand the current flow, and we're going to talk a little bit about current flow of the arcing currents and the clearing times. But 1584 2018 is that which we use to calculate incident energy, and they do it in 5 steps. There's 5 basic steps that we follow when we're doing our 1584 calculations. So just to give you a for instance, let me just get my computer working here. Okay, all right, it's working again. So the first step is we have to understand what the three-phase bolted fault current value is. Then remember, we talked about short circuit currents on last Monday. Okay, and this is why that last week was an important week for this, and I will redo those. I will redo that, but the YouTube videos for last week are up on my YouTube site. But I helped you understand what we mean by a three-phase bolted fault current, zero impedance. We calculate that at the equipment. The second thing we do is we plug that data plus other data with regard to the configuration of the bus, the distance between electrodes and all that good stuff, and we get a minimum and maximum arcing current. And then we determine the clearing times for both of those. And then with those clearing times and those arcing currents, we calculate an incident energy value at both of those arcing currents, and we pick the highest of the two. So that's the basic process 1584 outlines to calculate incident energies, and that's the numbers that we use for electrical workers to dress. But for 24067, we only need the first 3 pieces of the pie, or puzzle, whatever you want to call it. So those are the first 3 pieces that we need. We need to calculate that fault current, we need to calculate the maximum and minimum arcing current, and we have to determine the clearing times for both of those. So the tools we have for calculating the 3-phase bolted fault current, there are many. We have the Bussmann FC squared. Can you use that? Sure you can. It does give you a little bit conservatively high of a number, but you can still use that number. And in fact, if we have even if you're using infinite bus, there is an IEEE paper, which I will put in the links down below to this YouTube video. We have an IEEE paper that our Eaton Engineering Services Division wrote, which helps us understand that you can take, like if a utility gives you a 3-phase bolted fault that's based on infinite bus, you can cut that in half and use that for your arcing current calculations. But I highly advise SKM, Easy Power, any of those software applications. That's really what you want to use in these applications, especially if you're downstream in a power distribution system. But these are some of the tools that you have to calculate that. Now, I said minimum arcing current. That is not a 24067 requirement nor a 24087 requirement. I highly recommend that you do that because that is really your worst case scenario. So now to calculate arcing current, there's again a lot of tools. I showed you one. One of my tools, one of the Busman tools, Eaton's Busman division, that basically helps you calculate those arcing currents based upon available short circuit current. I love this stuff. So this is right in my wheelhouse. And if if you have any questions on it, let me know. But you leverage those tools, and remember, I told you in the beginning, these are some of the key components that will impact your arcing currents. Frequency is obvious. IEEE 1584, the limits are 50, 60 hertz. Obviously, voltage, we already talked about the pressure. The electrode gap, we talked about that as well. And that's the distance between the conductors, the buses, and things like that. And every piece of equipment may be a little different. And then you have the electrode configuration. We're going to talk about the electrode configuration because that's new in 1584. You have what they call vertical electrodes in a metal box, VCB, and that's typically your panel board applications, where you have, when you open it, when you take a dead front off of a panel board, what are you looking at? You're looking at flat metal buses. You're not looking at the front of those buses. You're looking at the bars. You'll see that copper or aluminum bar perpendicular to you. No, in parallel with you. Yep. So that it's up and down. So and that's what you can see there. Now, when you have a vertical electrode with a metal box with an insulating barrier, that's when you get down towards the end of that bus or the conductor, the energized part, where it's close to an insulated, like maybe there's an insulated plate or whatnot. For the most part, VCB is what you would use. I believe the worst case is VCBB, which I would just default to. Difference isn't that much. Then you have horizontal. This is when that bus is looking right at you. And I'm telling you, if you're an electrical worker, this is the worst case for you because that's the energy. Remember, the arc always flows away from the source down the bus. And if the end of that bus is pointed right at you, it's coming right at you. When you look at the vertical bus with barriers, the arc flows away from the source, which is down that bus, and then it flows into the barrier, and then that little plume pushes out. When you are looking at this, it's coming straight out at you. There's nothing barriering it off or anything like that. So this is your worst case from an incident energy perspective. And from an arcing current perspective. Vertical electrodes, that's in your open air. So these are the different types of configurations that you can possibly have when you're calculating incident energy and arcing currents. So these are your range of the model of 1584. You have 208 volts to 15,000 volts, so we're good in voltage. We have frequencies 50 or 60 hertz, and hopefully, I don't know if there's anybody on the phone who works outside of 50 or 60 hertz, but this model only applies in that range. And there's your limiting, there's the first critical factor. It's from for 208 to 600 volts, you go from 500 amps to 106,000 amps. That's presents a challenge in 24067, which I'm going to hopefully help you understand. And the way that we use how like your SKM systems analysis studies and other similar, even 70E recognizes Ralph Lee model, 1584 recognizes that Ralph Lee model. So most of your studies will reference the Ralph Lee model, but Ralph Lee model does not calculate arcing currents. What the Ralph Lee model does, it takes the three-phase bolted fault current and it compares it with the clearing time of the fuse or breaker at that three-phase bolted fault current, and then it has an equation to calculate incident energy. It doesn't meet the requirements of the NEC because the NEC specifically says arcing current, and the only thing I have to calculate arcing current is 1584. That presents the challenge. Now, the Ralph Lee method was a paper that I was presented back in 1982. It established a relationship again between the temperature and this. Remember, 82 precedes IEEE 1584, which the first edition was 2002, and then the next edition was 2018. So 1982 is well before the IEEE 1584 came on the market. and again, it's recognized in 70E as a method to calculate incident energy. It doesn't establish an arcing current value. So again, it uses the three-phase bolted fault current value. So, and I mean, you could, if you calculated incident energy on these fuses and you can say, look, it's less than a calorie, go away, leave me alone. You could probably get an AHJ to accept that. But I'm an engineer, and I'm sitting there saying, I know a little bit more about these trip curves. And I know that in some cases, that arcing current's not going to be clearing as fast as what Ralph Lee's method says it will. But in any case, that's just me talking. So now, I already showed you this screen, and I can tell you that for that 1200 amp fuse, the arcing current has to be greater than approximately 14,000 amps, which if I reverse engineer the solution and I use IEEE 1584, I actually used SKM, I can tell you that the bolted fault current has to be greater than 24,000 amps. Now, having said that, the chances of you applying a 1200 amp fuse when you have fault currents less than 24,000 amps are probably slim to none. You're probably going to end up using a circuit breaker in that application. But if you have a fusible solution for whatever reason and your fault current, bolted fault current, is less than 24,000 amps, you're going to need an arc reduction technology. Now, again, that's at 480. At 208, now you're into a different scenario where you could have a 1200 amp fuse even at these higher bolted fault current values. This is a 480 volt value. So what I'm doing is I'm pulling together tables to help the industry. We have that tool that's on the market right now, which will do both the 480 and 208 and 600. You guys in Canada got it good because you're at 600 volts. We love 600 volts. You love to push that fault current. You're going to have larger fuses without an arc reduction technology because that fuse is going to work for you because you're pushing current. Love current. You know what fuses eat? You know what fuses eat for breakfast, lunch, and dinner? Never gain weight. The more of it that you give them, the more they love it. Current. All right. So SKM, I used SKM. That's the basic model. And that was the one-line diagram. What I'm going to do is, rather than show you these slides, I'm just going to pull up I think I have it open. Yeah. I'm going to pull up my SKM. I'm living dangerously right now. So this is my SKM model. I have a, let's just zoom all. I've got my utility. I've got a conductor here, but this conductor is, I've got 750 kc milled, 25 in parallel, and only 1 foot because my goal is not to, show something that's realistic. I just want to create a fault source through a fuse to a panel and show you the clearing times. So if I run I'm going to run my balance system study, short circuit. I run my calculation, and then I'm going to run an arc flash and evaluation. So here's both of these scenarios. I got my fuse scenario is bus 3 and bus 6 is the breaker scenario. So I have an available short circuit current that's passing through that fuse of 99,860 amps. And my arcing current is 40,870. This tells me my clearing time of the fuse that I have in place, which I'm not sure what that fuse size is. Let's take a look. This is a Bussmann KRP fuse, which is a 601 amp fuse. We're going to change that shortly here, and I'll show you what it does to the incident energy. My incident energy is 0.46 calories. My clearing time is 0.0042. So here's what I'm going to do. That's my fuse curve. This is my fuse curve. I'm going to move this curve to the right. I'm put a 1200 amp fuse. My incident energy went up to 0.81. My clearing time went up to 0.0083. I'm going to increase this to a 2000 amp fuse. My incident energy went up to 0.92. My clearing time is now 0.0083, 40,000, 40,000, 40.87 kiloamps. I'm going to move this up to a 3,500 amp fuse. Now my instant energy is 24 calories. My clearing time is 0.257. This is beyond the 0.07 mark. That's this number right here is why you have 240.67. My incident energy for a clearing time of 0.2 seconds is 24.8. I'm going to move. This is for 100,000 amps, approximately 100,000 amps of fault current. I'm going to move this to the largest class cell, 6,000 amp fuse. I'm up to 220.4 calories. I'm longer than a clearing, longer than 2 seconds. So 40.87. Let's take a look at what 40.87 is. 40.87. I'm gonna add that in here. 40,870 amps. There's my 40,870 amps. Look at my clearing time is upwards of, it's over 2 seconds. It's somewhere between 2 and 3 seconds. Now, if I move my trip curve, if I lower the size of that fuse, look at where my arcing current's now tripping faster, a little over 0.01 seconds. That's why my incident energy goes down. So now what I'm going to do is I'm going to take this utility, and instead of 100,000 amps, I'm going to make it 106,000 amps. That's the limit of 106,000 amp, which is the limit. I'm going to do a run, balance system study, run. I recalculated my fault currents. I'm going to rerun my flash study. Now my protective device is 0.11, 480 volts, 0.25. Let's go back to this. I'm changing. Oh, wait a second. Go back to my one-line diagram. I think I screwed up. Yep, I have 106 amps. I have 106,000 amps. Boy. See, that's what live TV does to you. 106,000 amps. Rerun the study. Now I'm right. 37,000 amps. My arcing current is 37,000 amps. And the same fuse size, I'm at 10 calories. I've reduced the calories on that because my arcing current just went up. It didn't go down. So lower my fuse size, lower my incident energy because I'm into that region of the fuse curve. So I'm just hoping that this helps you understand the relationship between that trip curve and the arcing current and what you're looking for. And you can get your data of clearing times right out of SKM because it will give you your worst case clearing time in this screen if you're an SKM user. If you're not an SKM user, I'm sure that Easy Power and others have similar screens for you. So that was my that's sort of how I came up with all the numbers, and I just showed you what I did, and I kept increasing. So I'm going to go straight to the table. So I developed this table, which what you can see here is I have my bolted fault currents down here on the left-hand side. I have all of my fuse sizes up here across the top. Okay. Those are all my fuse sizes across the top. That's my bolted fault current down the left-hand side. There is my minimum arcing current coming down the left-hand side of the screen. So what I can tell you is, and this is what we use for our tool, I know that for a 1200 amp fuse, I need at least 21,000 amps of bolted fault current to get into the 0.07 second time. And you'll notice that, and now this is 480 volts. This isn't a 208 volt. I don't have a table for 208 volts, but you can use the app. So as my fault currents go up, or as my fuse sizes go up, the bolted fault current values that I need gets larger. And at the 3,000, at 480 volts, it's right at 3,000 amp fuse range is where I start to need more than 106,000 amps of bolted fault current to get what I need into the instantaneous region or into a 0.07 second clearing time for that fuse. Now, the question is going to be, what do I do about that region? I have an inspector who wants to see an arcing current. I have a design that has, say, a 4,000 amp fuse, and I have 150,000 amps of available fault current. What do? Well, you're either going to put an arc reduction technology on that, or you could split that 4,000 into two 2,000 amp fuses. And if you do two 2,000 amp fuses, I know, because the 2,000 amp fuse is right here, that all I need is 24,000 amps of bolted fault current. I could show this to the inspector and say, look, a 2,000 amp fuse has a clearing time of 0.07 seconds and faster when the bolted fault current is at least 24,000 amps. You have 250,000 amps in your project. So whatever the arcing current is at 150,000 amps, it's going to be greater than what the arcing current is at 24,000 amps. So that will give the inspector something they can understand to say, now I know you're going to be clearing faster than 0.07 seconds, because for a 2,000 amp fuse, anything greater than 24,000 amps gets you into that region. Now I believe that is something that can be logically understood, and it is technically valid. But now you're throwing two 2,000 amp fuses instead of using one 4,000 amp fuse. And I'll give you a method to say, if you wanted to keep that one 4,000 amp fuse and you apply an arc reduction technology, you're going to have to show them that the arcing current is in that region. And I'm going to show you how to do that here in a second or two. Again, opportunities to serve multiple feeders. We have now rules that lets you do multiple feeders and numbers of supplies, so you can leverage these to take that one 4,000 and split it into two. And we talked about those yesterday. This is just a table format. I'm not going to walk through this because I basically already did that. This is just the raw data that I used to generate that screen. So I'll just arrow through these so that if you're watching it on YouTube, you can actually pause it and take a look at it. You can pause the video and look at it. And I'm showing the arcing currents, the bolted fault currents, and the actual clearing times that SKM put out for me. And then I'm showing you, obviously, that where the Lee method for a 480 volt system takes over. So I can say that if I have a 1200 amp KRPC fuse, no arc reduction technology is required as long as the bolted fault current is greater than 21,000 amps. In this region here, again, I'm going to give you some thought process. Again, there's no available equations for that. We have, though, some methods to be able to handle that. And we already talked about the Lee method. And you can always pause this video and read that. I'm just going to walk right through it. So if you meet these two things, if you have a fuse 1200 amps and greater and your clearing time is 0.07 seconds, you're good to go. Document it, give it to your HJ. Use the tools that are accessible. Use SKM. You can help and use this 24067 tool as well. Again, the conservative approach is to require arc reduction technologies for any fuse applied at fault currents greater than to require arc reduction technology for any fuse, again, for a 480 volt, 3,000 amps, and greater. For a 208 volt, you're at about, I think it's around 1,600 amps. I can't remember. But I could, like I said, if I had a 2,000 amp fuse and I had 180,000 amps, I can show you that I don't necessarily need to employ a technology because that arcing current is going to trip fast. Now, when I'm above 106,000 amps, what I did here is I calculated the arcing current at 106,000 amps at both 208 volts and 480. If you employ an arc reduction technology, you'll have to make sure that it can actuate based upon the arcing current at the largest bolted fault current that we can calculate, which is 106,000 amps, which is for a 208 volt and a 480 volt system. Those are the numbers. I didn't do a 600 volt system. I can do that, but I'll do that later. But this is, if you're on a 480 volt system, make sure your arcing current, your technology actuates at 42.2 or greater. And if you're at 208, make sure you are actuating at 208 or at 16.8 or greater. I think that's logical. I'd love to know opinions, throw it up there in your chat sessions and mull it over in your head. Maybe think about it tomorrow. And then come back with me with the, hey, I like it, or Tom, you were drinking too much that day. All right, so you have to document it. Single line diagrams shall identify all the 1200 amp fuses. All you have to do is identify where you have these 1200 amp fuses. And then this is new for 2020. You have to document and show that your method to reduce is will clear at the lowest, at the arcing current. I throw in the word lowest. Probably a good suggested change. Again, you could take the form of a trip curve and an arcing current, plot it on there, and give it to your inspector. You can do that comparison. You can use the tool that we have to help him understand, and we're going to have a report available with that regard. You got to calculate the fault current, calculate the arcing current, compare those two, leverage this tool. You can get a report, email it to yourself, all that good stuff. I already talked about the methods. I already talked about the tools, and talked about the arcing current analysis, the 1584. We already talked about the 106,000 and the Ralph Lee. I think I've just repeated myself here a little bit. I'm just going to walk through this to get to. Hold on, let me just. I've got some duplicate slides here. Let's go to the methods. All right, so now we're into what are the approved methods. If you need to put an arc reduction technology, the methods that for 24067 are differential relaying, energy reduction maintenance switch, energy reducing active arc flash mitigation system. So let's talk about the zones of protection. We had this on one of our quiz. Differential relaying, the way differential relaying works, the gazintas need to equal the gazaltas, okay? So whatever goes into this zone and current has to come out of the zone and current. There are CTs at the top and the bottom of these drawings. That's a current transformer. This is a current transformer. Anything that's going into that zone has to be accounted for when it goes out of that zone. And this relay, and it will tell you when the current going in doesn't equal the current going out. So that's how differential relaying works. It doesn't recognize any faults downstream. The energy reduction maintenance switch, since it's just based on current value, it will look as far downstream as the impedance in the system will let it look. But it basically will shunt trip a switch and open that circuit for faults downstream. This is an energy, again, reduction, and the active energy reduction system. So I'll have a video of that a little bit later. It, again, has a zone of protection. So if you're working down here, you don't get protection because it's only looking up there. This is not differential relaying. I keep telling myself I need to fix this. This is the electronically actuated fuse. Electronic fuse. What happens here is you have the sensor on the secondary, and it's a medium. Right now, the only place this exists is a medium voltage fuse. You have a CT here. You have a brain here, the relay. When it determines that your current value goes greater than a certain number, it will tell that fuse to open using pyrotechnic, right? It's not a Star Wars thing. It's a charge inside that fuse, and it tells it when to open. Now, performance testing. There's a new requirement that says you have to verify that this equipment is functioning on installation. I don't recommend that you test that the fuse works. Okay, I don't recommend that you inject current through the fuse to watch it open. I mean, my busman sales guys would love that, but you don't want to do that. But you do have to do just like we do with ground fault protection of equipment. That's in 24067. Remember, or I'm sorry, just like ground in 23095, 24067 has the requirements that you have to performance test by primary current injection test or an approved equivalent means or another approved method when first installed on site. It's similar to GFPE. You're going to make sure that whoever's doing it is qualified. And I would say that if you're out there doing primary current injection testing on your GFPE, you're going to want to get this done at the same time. Don't let him go out and do 23095 testing go home, and then have the inspector tell you, you need to get them back out there to do this testing. You need to have a written record. And again, some energy reduction methods can't be tested because it would damage the equipment. So like a fuse, if I try to show you and prove you that I'm going to actuate in 0.07 seconds, I'm going to open that fuse. You don't want to do that. When you have, you got to test the CTs, you have to test the electronics, any of the sensors. So when I have CTs in the picture, these are some of the tests we're going to be doing. Polarity test, verifying the ratio. If it's a 300:5, make sure it's a 300:5. These arrows, okay, those stickers aren't always put on the right way every time. We've seen them where they were not labeled correctly. So it's important to do it. You may not have to do a burden test. You may not have to do an excitation test. That'll, the guy or gal who's doing the testing will dictate what he does or she does. So if you're doing the energy reduction maintenance switch with a local status indicator, that is the fuse that's going to be doing, or that's the switch that's going to be doing the job. This is one example. The GEHBC2 switch is one example of a device that'll help you. This is the Eaton's switch that has a disconnect and a shunt trip, 1200 amp fuse, 0 sequence CTs. We've got solutions coming out every day on this type of thing. We have tools that you're going to be using to help you determine when to employ technologies. Okay. Primary current injection testing, you're going to verify the CTs. Here are some of the equipment that we use. This is a PCI 600, outputs of 1200 amps. It's like a briefcase size, easy to carry around, but the output's only up to 1200 amps. This is the DDA 1600, 16,000 amps of pure fun in the field. And how about, I got the other one is the Phoenix. I'll show you the Phoenix. That's another good one. I'll just show you a quick video. I think I have it queued up here. This is the Phoenix testing of a circuit breaker at doing primary current injection test in a lab.
For arc flash, we want to turn the instantaneous off.
So he's showing you, he's setting the, he's turning the instantaneous off.
Okay, so
and the camera guy should be shot here. It was me. I'm not that good at using a camera. But he's basically turning that instantaneous off. He'll turn the arm switch on.
Now we're going to turn the arc flash on.
He calls it arc flash.
Okay, we have settings R1 to R5. R5 being 2.5 times the rating of the rating plug. R1 would be 10 times.
So the arc reduction technologies are settable.
R5 rating first.
And so this this piece of equipment that you're looking at right here is the Phoenix, which is it's a heavy device. It's pretty sophisticated. Can put out a lot of current.
Okay, breaker's closed. So what we're going to do, 2.5 times.
So he's basically, and I'm not going to waste our time watching too much of that, but he'll inject current through here. This will open and trip. It'll tell you the current value that it tripped at, and then he verifies that it's functioning. That's typically how you're going to see these tests done in the field. Some sort of testing unit that's separate, and the breaker is going to be racked out, especially the breaker. If it's a fusible switch, the relays and CTs will be inside, and you'll have a piece of equipment that'll inject current. Now, my advice is you don't have to inject the full current. You can just inject enough current to make sure that the device is operating and functioning. You're not going to be putting 40-some thousand amps through that piece of equipment or that breaker. You're putting something that's much less just to make sure that you are functioning. And these test units are at a low voltage, so you'll notice, he doesn't have any PPE on because he's less than 30 volts pushing this current through this equipment. So everything in here nothing in here is going to be of a shock issue. This equipment's built that way and built for safety. Like me, built for safety. So the active arc flash systems, they all have instructions to tell you how to test their systems. The arc quenching system and the GE solutions. Every manufacturer is going to have something. And I'm just going to quickly walk through this to show you what some instructions include. These are all available. I'll throw a link down below to show you. I took some snapshots out of this document. They have step-by-step procedures. They tell you what comes in the box. They tell you what to do in step 1. They tell you what to do in step 2. They have good. I love whoever made this document. I'd love to just give them a high five because they covered all of the details. I hate instructions that don't have pictures. I'm a picture guy. I love to have a lot of pictures in my technical documents. That's I'm being on code making panel 2 and 10. I'm going to start making public inputs to add pictures in 240, 230, 210, and all that good stuff. So Connect, it walks you through step by step. This class isn't to make you proficient at testing an arc quencher. I'm just showing you that the instructions and the amount of information. We'll do training with people to qualify them to make sure that they understand exactly how to test these systems. You need a complete record of your testing. The electronically actuated fuse, again, it's activated via relay. There are ways to test everything other than telling that fuse to open, right? You're going to verify the CTs. With low current injection, you're not going to inject high current that you're going to tell that fuse to open, all that good stuff. Again, you're going to just make sure that everything that's technically working should work, right? So that is 240.67 and all this. Now, what I want to do is take some time and go through 240.87. Now, 240.87 saw some love. It too received attention with regard to the arcing current and making sure that the devices are set correctly and operating correctly. You have to remember why we are in this mode, because I showed you the amount of incident energy downstream in a piece of equipment can be impacted by the overcurrent device. And I always tell people to go to Donnie'sAccident.com. If you've never gone and seen Donnie's Accidents video, go to Donnie'sAccident.com, watch that video, listen to Donnie tell his story. The videos that he has were created by his wife when he was in the hospital because he didn't wear his proper PPE. We are in the business of arc reduction technology for the electrical workers. So I'm just going to take a second and take a look at some of the chats before I really get into 240.87. All right, there's the 43. Will you send PDH? Yes, I will send PDHs out. Nice tool. Thanks, Tim. Is there an assumption for over 1,000 kV just clears too fast to need arc energy reduction? No, that you're into a different world of when you're above 1,000 volts. That's a little bit. We can calculate arcing currents. We can use IEEE 1584. It's just not a code requirement at this point in the National Electrical Code. So that's the name of that tune. Documentation is the documentation to be provided by the design engineer or the contractor / manufacturer? Good question, Nancy. So that depends. If you're a design build contractor and you're doing your own work, you have all the tools to be able to do that. You can ask the manufacturer to provide that information, but I would say include that in your request for quote, right? Because that may change some of the numbers. There may be some math and some engineering services that would have to come into play to get you that documentation and do an analysis and create the documents that you can use to share with the electrical inspector. But I would say go into your design thinking about this ahead of time anyway. Is replacing a fuse installing a fuse? Don Denier, I love you, brother. Is replacing a fuse installing a fuse? That is a good question. And I know why you ask that. And he's smiling right now. I know Don very well. He's sitting in his chair. He's probably sitting on his hands smiling right now. 240.67 says, where fuses rated 1200 amps or higher are installed shall apply. It depends, Don. If I don't want to do any change to my system, then it's not. If if you know, that's a really good question. Honestly, is installing his question of is replacing a fuse, installing a fuse, you could probably make an argument both ways. You could probably make an argument both ways, and I would say that the NEC is not very clear in that regard, and I look forward to your public input. Is the documentation, we saw that one, not normally, in my opinion, David Shapiro says, but up to the jurisdiction. Yep, it's a gray area. Yep. So again, and that's why I say when the code is not clear, those are opportunities for an authority having jurisdiction, electrical inspector, to weigh in on the discussion. That is also an opportunity to make a public input. I'm watching the chats on YouTube. On YouTube, yes, this is a great presentation. So, Dan, do you still enroll in the class? Blah, blah, blah. Okay, I submitted a PI to address changing a fuse, and the code making panel didn't really answer it well. Ryan, you're probably right. I don't know. We'll have to take a look, and maybe I'm sure we'll see public inputs this cycle. Tom, can you briefly describe the correlation between 70E and 1584 calculations? Yes, so sure. Remember 70E. 70E is the. Let's talk about electrical safe work practices. 70E is the how. OSHA is the shall. OSHA tells you have to have an established electrical safe work conditions. You have to have a safe working plan and things of that nature. 70E is the document that says, here's how you get this done. Now, 70E tells us that we have to label equipment with an incident energy and working space and things of that nature. And we're supposed to use leverage resources and tools. And they reference in 70E, IEEE 1584, they reference the Ralph Lee method, they reference the Doan method for DC. So there are various methods to calculate incident energy. IEEE 1584 is a document made by engineers by actually IEEE. It was based on a consortium of people who pitched in money. They ran tests in a lab over and over and over and over to come up with equations. And those equations are used to calculate incident energy and arcing currents and things of that nature. So 1584 is the math behind creating the label. 70E tells you need to put that label on equipment so the electrical worker knows how to dress. And 70E will tell you how often you need to keep that document updated, which is based on 1584. I hope I did that justice. Yeah, very stiff electrical system. Yes, Tim. 83 MVA. Yeah. On secondary networks,
Yeah,
go ahead, Tim.
Yeah, Tom, that's very stiff at 480 volt.
Yeah.
That's why we have, 65 kA, bus bracing and 65 kA rated devices, because most utility systems are going to be less than 65 kA. And what you're looking at is probably a supply transformer, 2500 kVA. Now, on an industrial system or a spot network where you parallel transformers and you get 3000 kVA at 480 volt or 5000 kVA at 480 volt, you can see some of those 100 kA short circuit currents. But rarely on a utility system will you see one exceeding 65 kA unless it's like a metropolitan area or a spot network.
Yeah, like on a spot network, in your typical downtown systems at 208 volts, what do you see?
They can be anywhere. You can see them as high as 80 kA at 208 volts. It all depends on what particular city that it's in.
Okay.
And they can be all over the place. And usually they're nominal 208, but they run at 216 is really what they run at.
Perfect. Oh, really? Okay. Perfect. Cool. Thanks, Tim.
The spot networks are what are your 480 volt network, where you'll have a small area or group of businesses that you require that kind of capacity, and they'll parallel multiple transformers to get a 480 volt spot network, and those can exceed the 2500 kVA transformer capacity and exceed the 65 kA short circuit current on the devices. But typically you're going to see something less than 65 kA for almost all the applications industrial unless you see multiple parallel transformers or high transformer capacity.
All right, cool. Thank you very
Thanks.
much. Thanks, Tim. That was Mr. Crowshore. I told you, he's a smart guy. Awesome. That's what I love. Just throw it in there. Donnie'sAccident.com doesn't appear to be working anymore. Really? Well, that's ungood. I got to talk to Donnie. Let me just try it. DonnieSACCIDENT.com. DonnieS accident.com. Boy. Yeah. Oh yeah, it's up. I got it. I got it here. DonnieS accident.com. Woo. Yep. Donnie's still out there. I would think one for the one replacement would not trigger. Yeah, 1-for-1 replacements. But if you're changing the size of that fuse, yep. Thanks, WW. Okay, presentation. Please puts your presentation. Watch on YouTube. 150,000 in Dallas off of. Okay, there we go. Secondary network. So this is that what Tim was just talking about. When you start paralleling transformers, you're lowering that source impedance, and now you can get higher fault currents. And I've typically seen like this is 150,000. I know downtown Pittsburgh. Downtown Pittsburgh, you'll get like 150, 160,000. I had my friend in New York City tell me that they've had some 200,000 the secondary networks. So 100,000 plus from downtown Fort Worth area. There we go. The highest I ever saw was 210. Woo, Queens, New York. Joseph, wow. That's a biggin. In West Virginia, we call that a biggin. That's pretty cool. I'm going to take a look on YouTube now. It looks like we just got some simple dialogue going on. The quiz review. They don't based on my experience for this quiz. All right. So it works. And they were talking about the Donnie's accident as well. And Ryan mentioned about the PI. All right. We're going to move this train forward. NEC 2011. We already talked about this. I'm not going to dwell on it. It entered in the 2011 code. It's been continuously changed. And the big thing in the 2020 cycle is they clarified the arcing current and the clearing times. Again, where the highest continuous current, just give you that. Where the highest continuous current is set trip setting. So what they're telling you, they took this language from 23095 and other areas in the NEC where we talk about 1,000 amp devices in GFPE. So it's similar language that you've seen there. Let's talk about the impacted installations. Any installation where a circuit breaker's highest continuous current trip setting for which the actual overcurrent device installed in a circuit breaker is rated or can be adjusted 1200 amps and higher. So that tells us that if I can have a 1200 amp frame, if I adjust it down to 600 amps, I still need to employ it because I can adjust it up to 1200 amps. Now, during the code cycle, I presented to Code Making Panel 10 this graph to help them understand the impact of what they were talking about. In reality, and then I'm using our frames. In fact, our frames just changed because we came out with a new power defense line of our breakers. You got to check that out online. Power defense, we don't have the FJs and Ks and whatnot, so we have different numbering system, but pretty powerful release on our part. We even have condition of maintenance. I mean, that's pretty cool. Just think you can walk up to that circuit breaker and it could tell you how often it's been operated, cycled, all that good stuff, whether it's solved fault currents. That is critical for the electrical worker, but I diverge. N-frame, R-frame, and power breakers, those things can be adjusted up to 1200 amps. If I look at our N-frame breaker, this is an example. I have an 800 amp frame breaker that can be adjusted down to 320. I don't need an arc reduction because I cannot take that N-frame breaker up to 1200 amps. I have to physically change the breaker itself. But the 1200 amp frame breaker can be adjusted down to 500 amps, and I can still adjust it up to 1200 amps. I need an arc reduction technology in that breaker. Power breakers, or I'm sorry, this is the R frame, still a molded case circuit breaker, goes up to 2500 amps, and all of those can be adjusted to 1200 amps and above. I love the dialogue going on YouTube too. All right, so this is our insulated case circuit breakers. these devices are all pretty much going to have an arc reduction technology as well. Larger frame molded case circuit breakers, insulated case circuit breakers, and power circuit breakers that can be adjusted to 1200 amps and larger. Check the trip unit, check the capabilities of the devices that you're looking at. That's going to be critical and very important to determine whether or not you are into a technology requirement. Documentation, demonstrate that the method to reduce clearing time is less than the arcing current. That's the big change in the documentation. So you've got to show that it will activate at the arcing, and I keep saying the lowest arcing current, not, I mean, we weren't that clear in this, but it should be the lowest arcing current. Okay, we need to document where these devices are, and we need to document that they will respond to those arcing currents. And this is just a picture of the instantaneous pickup, right? This shows you your instantaneous region on this circuit breaker. Starts just about right here. You know, now you're into the fast clearing time. And it can be very high. I mean, look at this, 17,500 amps on that breaker. That's pretty high. There's your instantaneous region. So your documentation could say, here's a plot of my current. Here's a plot of my arcing current. Look, I'm in the instantaneous region. I meet the requirements of 24087 or the arc reduction maintenance switch. You can plot those curves and show you meet it. Remember, arcing current is a new term. It's not defined. And I'm not going to go through the same slides that I went through on the other. So I'm going to save you that misery. And I'm going to skip on down to the approved methods. Okay, you're going to see some writing in here that from my last time I used these slides. So again, this is your instantaneous trip setting. And now here's an important thing that they did. They wanted to clarify, because there were a few people going across the country saying, oh, by the way, you know, you can just roll down instantaneous and meet the requirements of 24087 and roll it back up again. That is a no-no. For 70E purposes, you don't want, you can't be changing set points in the field like that. If you roll it down, you don't know where you rolled it back to. And sometimes all of these trip units, they're all different in what they look like. So they added this language right here that says, temporary adjustment of the instantaneous trip setting to achieve arc energy reduction shall not be permitted. You set it and forget it. And then you have the instantaneous override. The instantaneous override is not adjustable. So in a lot of cases, especially if you're not worried about selective coordination, you're probably going to meet this requirement. If you're especially if you're series rating things, right? If you're not worried about where the fault current is, as long as it's less than the interrupting rating, the arcing current rating could be in the instantaneous region. You're going to have to go through and make sure that's the case. And if it's not, if you're doing selective coordination and you're pushing these instantaneous values to the right further and further because you have to add intentional delays. We talked about selective coordination on Tuesday. If you're worried about not taking your entire plant down and you're adding intentional delays on the service entrance equipment all the way up there at those big boys, the big devices, they're big because they can hold those contacts closed. We're going to learn that on Thursday of this week. Then you're probably going to need an arc reduction technology. So based on the available arcing current, we already talked about that. And we already talked about the methods. We talked about the, I don't want to waste everybody's time about repeating the same thing. So I'm going to move into the different methods. We talked about temporary adjustment. Now we're going to talk each area, zone selective interlocking. And I'm going to talk to you about how ZSI works. And I know it's not going to be the same thing that you've always heard, because it doesn't get you selective coordination. In a ZSI system, that main device is what does the action to clear the fault. And it actuates on its short time delay pickup setting. So what you're going to have to do to meet this code is you're going to have to ensure the short time delay pickup setting is less than the arcing current. You're going to have to make sure that for the zone selective interlocking to work, that device's trip curve is short time delay setting is to the left of where your arcing current is. The way we wire these up, we wire them all together. We wire this is the most simple configuration. And the zone of protection is right there. If I have a fault down here and I didn't coordinate these two devices, and the fault current is greater than the instantaneous pickup of that feeder breaker and greater than the instantaneous pickup of that main device, they will both open. I don't care about ZSI. They will both open. What ZSI gets you is when I have a fault inside here, that's when this main device ignores the settings that you gave it for selective coordination and goes without an intentional delay. That's what ZSI gets you in the zone of protection. Any fault in that zone will trip without an intentional delay, but because of the brain we talked about earlier, it'll typically take around 0.07 seconds. Now, nobody's asked the question. I haven't seen it. Where did 0.07 seconds come from? Right here, you're looking at it. This, when they originally talked about for fuses, they were going to say that the arcing current had to be in the current limiting region of the fuse. And I think Vince Saporito was sitting at the table and said, hold on. We have a requirement on breakers for zone selective interlocking that will give you a 0.07 seconds clearing time, but yet you're going to tell the fuse it has to act faster than some of the slower technologies that are in 24087. So then the panel said, you know what, you're right. We can't hold one to a higher standard. So that is where the 0.07 seconds came from, because your typical clearing times for ZSI, zone selective interlocking, are 0.07 seconds. And that's all I have to say about that. That's where that came from. You don't get any protection outside of those zones of protection of things. So if you're working, if this feed is supplying a panel board, and you look at this arc flash energy inside of this equipment, it says this is 2 calories, and you're looking at this one and it says it's 18 calories, and you go, well, wait a second, I have an arc reduction technology up here in my main equipment. How can it be greater? It's because you're basing the clearing time off of that feeder breaker and your lower fault current, so you're not getting protection from the zone selective interlocking. So that's basically what these next slides tell you. You know, anything that's downstream is outside of the zone of protection. The gazintas equal the gazaltas. That's the way I was taught in school. You know, those two devices know it, and they all go by their program settings, but if the fault is internal, the upstream device knows the downstream device doesn't see that fault, and it trips without an intentional delay. So this, on a trip unit, this is your short time delay pickup. That's the setting that's going to be critical for that main device that tells you whether or not it will actuate in the arc reduction as an arc reduction technology. And that's what it looks like on a TCC curve. There's your short time delay pickup. Your arcing current in this case has to be greater than 2.4, because usually these can go about, if that's a 1200 amp device, the pickup of short time delay is around 2 times 2x, 2 times 1200, which is 2400 amps. And you always got to be on the plus side of that, because there's an error margin. There's a plus or minus associated with it. All right. So this challenge is knowing that it's actuated. We have a system right now. Eaton, I think, is the only one who has an activation. So we'll give you indication that zone selective interlocking is working. And we have methods to test ZSI, because you have to do the performance testing at installation of all of these technologies I'm walking through right now. You're going to have to show that they are functioning. Differential relaying is the same thing that we talked about over on the 24067. Same. The only difference is that you don't have ZSI when you're using fuses. And it's the same differential, so I'm not going to cover that again. You have to verify the CTs. You've got to verify those labels. They may not be right. Make sure you have and make sure you have a metering class. Or is it a metering class CT or a relaying class? Metering class CTs will perform a little differently. They'll saturate at your higher fault currents. You're going to need a relaying class CT for these things. Don't screw that up either. or don't mess that up. Right? And then you have zones of protection. It's important to understand the zones of protection and what you're getting. Now, the energy reduction maintenance switch with local status indicator and a compass in the stock. That'll give you the protection downstream. We already talked about that. In the other, same method, same technology used on fuses. Okay. How far downstream? It depends upon the impedance. Now, here's what I like. Whenever I do, my suggestion to everybody, I know we have some buttons on our breakers. My suggestion is to create a little panel like this. And you know what I love about this button right here? You can open that door, you can close that door, and you can put a lock on it. And locks are good for lockout tagouts. Now, I know you can put a lock on some of our face plates and things of that nature, but this is really nice. You got a nice big blue light. It really shows you when it's on and when it's off. It's there for when we're in maintenance mode. The electrical worker will love you for it. This is basically what it does. It takes this short delay curve, and when you turn it on, it adds this nice, and we go faster than this. I don't know why. You know, I love my engineers. I love them dearly, but we always show 50 hertz or when it's the warmest or when it's the coldest or all this other good stuff. But we go pretty doggone fast. Now, the active arc flash mitigation system. Got a treat for you. 85,000 amp arcing fault. That is humongous. You don't want to be in front of that. 85,000 amps. We're showing that will just rip through equipment. It'll take months to repair this application. Now we're going to do the exact same test with an arc quenching. That's the exact same test. It operates faster than around 0.004 seconds. You can be in front of that gear and have that go off. You can have the doors open. You might have to change your shorts afterwards, but you're not going to go home injured if you have the technology in place to take that type of fault by simply putting a blue box in there and a relay together, working in connection with each other. All right, so I'm gonna pause this next portion of this video. All right, so let's take a look at what just happened. This little blue box right here. This blue box right here is the arc quencher. This little relay right here is it senses. There's light sensors inside this box enclosure to sense the arc. When that relay senses the arc, it tells that blue box to activate, which causes a very low impedance. It's not a bolted fault, but a very low impedance, sucks the energy inside that blue box, basically, and it tells the main device to open. And all of that happens in 0.004 seconds. Tell me that ain't unbelievable. Don't tell me that ain't unbelievable, because I think it's unbelievable, but the video's worth 1,000 words. And I love the front shot of this because it just demonstrates why technology is really advancing in this world of arc reduction. I still say there's no reason for anybody to die from arc flash nor shock because we have the technologies to reduce that. It may not be a code requirement. We can go above and beyond code and meet the requirements of our customers. All right, so that's the active arc flash mitigation system. You can't field adjust the instantaneous. Again, that's your instantaneous. Adjustable instantaneous should not be modified in the field. You know, you take a look at the different types of devices in the marketplace. Every manufacturer's, a person looking at this might not realize. They might think that, well, the one on the left is the long time, the one in the middle is the short time, and the one on the right is the instantaneous. No, all of those are instantaneous. All of those dials, all three of those dials are instantaneous pickup only. Dialing down the instantaneous, is not an approved method to meet 24060, 24087. That is not a good thing. It would be ungood. All the terminology, how do you know which one of these buttons is instantaneous versus short time delay versus long time delay? It's every manufacturer is going to be different. Okay. Some trip units are pretty nice. They give you the whole trip curve right on the face, but some of them are digital electronic. You know, that's just, you don't want to be modifying these things in the field. Turning a switch on and off does not equate to field adjusting the instantaneous and vice versa. Right. So the instantaneous override, you'll understand what an instantaneous override if you show up on Thursday. And seeing if there's anything else. Approved equivalent means. Let's end on this one. If I have my new Van Ducky, one of the methods that I would use is to say you could calculate an arc flash value based upon this new technology and compare that with the incident energy calculated with, say, zone selective interlocking or differential relaying or whatever the other technologies that you're using. Or you could say, here's my pickup points for my technology and compare those. So those are just the different areas of that you can, different ways that you can just help the inspector understand when your new technology is should be permitted. And the last thing I'll say is 24087 also has performance testing. It's just about the same as what you have over in fuses. So going through this is really a regurgitation of exactly what we covered outside of zone selective interlocking, which was not in the fuse section. And for ZSI, we have a whole bunch of, here's the performance testing. Here's a document that we have for zone selective interlocking. I mean, they even show the guy's hand, and they walk through everything. Here's how you open the case. Here's what should be in the case. Here's where, remember to plug it in. Okay. I mean, here's how you have your zone 1s and zone 2s. There's how you plug it into the face of the breaker. You move the selector switch on the ZSI. So we walk people through simple and complex zone selective interlocking testing, which can be complex. This is the simple method, which shows just a main breaker with feeder breakers. This would be the complicated method. You have a main time main application, and you've got to make sure that all these things work. Go back to the manufacturers. You're permitted to do that as part of 24087. It says primary current injection testing or an equivalent means. And these are the reasons why that equivalent means is in there, because these things can be very complicated. This is not GFPE. This isn't I'm just going to go out there, inject some current and be done. These things can be very complicated. You're using tools. You're not going to just run current through the arc quencher. Okay. You're going to buy another arc quencher. It's just like it's similar to a fuse but we have test methods to test the arc quencher, like I showed you earlier on 24067 discussion. So these things are complicated. You're going to want to do this all at the same time. Get your ground fault protection of equipment testing done and get this testing done all at the same time, because if you don't, you're going to probably have to have somebody come back out and redo it for you. And if you didn't plan for it in the budget, I think we all are pretty savvy enough to know that when things aren't planned for in a budget, that would be not a good thing with regard to having to pay somebody to come all back out again to do some more testing. All right, so that is pretty much what I wanted to cover today. It's 1:58. And that's a good thing, because we got through a lot of material in the amount of time that we had, 2 hours. And now you see, 2 hours went fast. I don't know about you guys and gals, but 2 hours went pretty fast. So I am going to get to the end of this slide deck. Go back to I'm going to discard my changes. That's probably why I keep forgetting to make the changes to the slides, because I'm discarding all my changes. Never said I was the sharpest spoon in the drawer. All right, so I'm going to show uh, the Mentimeter. This is the final exit points. While I have that up, I am going to read through some of the chat sessions. For any wiring corrections between devices, is there requirements for ensuring the integrity of the wiring? I mean, when you do the test, that would give you an indication that things are working. Now, we have a requirement on initial testing. The second thing, the other question I usually get is, what about after the initial install, right? How often should we be testing these things? And that's really a 70B, as in Bob. Remember the trilogy? 70, 70E, and 70B. 70B is on maintenance. 70B is an important thing. So you should be periodically testing your zone selective interlocking. I know that our products, Eaton products, have now an indicator to show that ZSI is active and working and things are working fine and there's integrity there. Not all technologies have that, or not all manufacturers have that. So that's why periodic testing is going to be really important to make sure that, and you know, a lot of this is secondary current injection testing, so you're not ripping things apart. Send us an invitation for Thursday's session. I will send that out. It is, I will send that out to everybody on this call for that request. Yes, a locked cover is one of the methods that is permitted to be used to restrict access to adjustable trip setting. That's right, Don. Then you default to the requirements of 240.6. Oh boy, I gotta scroll up on this. I got Kirchhoff. These guys on the chat session are talking Kirchhoff. Kirchhoff's laws, awesome. It's day 4 now, Thursday. Oh, Sean. You know what? If you guys want to operate outside of, I already have 12 to 2 for breaker basics. I could do after that, like say 3 to 4, but that'll tie you guys up for like 4 hours. I was thinking of moving it to Monday. Send me a note on what you guys want to do about Friday. If you want to just hold Friday, let me know. If you want to delay it till Monday, we can do that. If you want to do it Thursday evening, I can do that too. Like Thursday afternoon after this, let's say 12 to 2, we can do breaker basics. And then maybe 3 to 5, we can do code changes. Send me a note, send me an email or something like that. I'll send you Thursday's note, and you guys can respond to my email with what you want to do on Friday. Okay, David C 240.6b. I don't remember looking inside service inbox for that job. Do these dial a current breakers have any requirements for sealing after setting? That's where they're, yep. So there's a cover that has to go on in a seal. A lot of times people don't put it on there. We talked about 480 to Queens is 208. Yep, there we go. Sacramento. The dial a current breaker have any, okay, so dials David C 240.6B and C. 240.6B and C, I believe that's where the cover is. 240.6, it's in the general requirements. 240.6B, adjustable trip circuit breakers, the ratings of adjustable trip circuit breakers having external means for adjusting, restricting access. So C, that's the one that tells you they have to be behind locked, located behind removable and selectable covers, etc. So, yep, it's a good reference, Mr. Ganir. Thank you very much. All right, so I see many of these with no provisions for seals in the field. Mr. Platt. Yep. Requires the conductor ampacity to be equal to or greater than the maximum adjustable setting. So if there's no seal, Don's point on, so the discussion on the WebEx chat session is about this seal, and you have C, which talks about if you set that breaker for a lower value, say it's a 1200 amp breaker and you put 600 amps worth of conductor on it, you're going to lower that setting to 600 amps and then you have to seal it. to make sure nobody changes that number, because you only have 600 amps worth of conductor. If there's no seal on the breaker, you can't adjust it down to 600 amps. You have to make it to Don Ganier's point. You got to go to 240.6 A or B, and you have to basically make it so that the conductor is the same size as the maximum setting on that circuit breaker. Good discussion. All right. If for any wiring connections between CSI, is there requirements? Okay, I second Gabe's. I'm going to see if we got how many. We got still got 213 people on YouTube. Thank you very much. Monday, move it to Monday. Okay, I'm going to move. I'm just going to move it to Monday. Yeah, 4 hours is way too long. I agree with Gabe and other people. So, can you make it a question for Menti? Oh, I sure can, Keith. I'll do that. I'll send it out. I'll do a little vote. My suggestion is to move the breaker basics. Oh, do the Nihad. Wow, Nihad, bam, comes diving in. He's saying move the breaker basics. I'll make that part of my Menti questions. And that would be 4 straight days on code changes. Yep. Will you be posting these presentations somewhere we could get access to them for later references? Will you? Yeah, so here's what's going on. It is on YouTube. These presentation slide decks, there's a ton of these slide decks. The quiz is on 84, 21, 47. So hold on, let's make sure that that's working. Monday code, happy Easter. Thank you, Charlie. I appreciate it. And I'll tell Bobby Joe you asked about her, and tell Janie we said hello too. Thank you very much for dialing in. Miss you, buddy. Really do. Miss you very much. I'm putting these things on YouTube. I have all of last week's up on YouTube. You know, subscribe to my channel. You may not be able to see it at home, but you can, or I mean at work, but you can definitely see it at home. You can get it on your phone, the whole bit. You can scroll, you can pause. To take all of my PowerPoints and PDF them would be a nightmare. All right. Okay. So I'll put the Mentimeter out to see if you guys want to move breaker basics to Monday and keep the code changes through Thursday, or move the code changes from Friday to Monday. I just figured it might be good to do a break. All right, so I'm going to check Mentimeter out to make sure that I'm getting people's names in the final quiz or final tag out. I'll tell you what, doing the certifications last night, you guys better love me, because wow, it is a manual process. But and I did over 200. And now I'm looking, I got over 300 taking this quiz. Praise the Lord. All right, I must really love you guys. All right, let's take a look at what Excel is doing for us. I'm going to take a look at the chat. Yeah, okay, great. So everybody's putting their stuff in there. I see Mr. Abbasi, New York, well represented. Hopefully my local 98 guys are represented. I've got 312 people took the quiz. Hopefully I'll have 312 who entered and make my life a little easy. Everybody's voting on Monday. 98 in the house, y'all. Great. Thank you, Lewis. Appreciate it. Love you guys, and stay safe, please. Chris, thank you. Thank you very much. Not a problem, Lou. Everybody's having a good time. So let's take a look at the live stream. I don't know what it was. I figured out the live stream thing. I've got a really good connection. Peer reviewing a one line having multiple 4,000 amp services with assortment of equipment and overcurrent protective devices type, OCPD types. What is fair comment at this early design development stage to make for selective coordination? I would ask the engineer to Nikhil to send me an email. I would ask the engineer. So here's what we do in the design phase. Fred, I would ask, put the, I don't know if you're the engineer or you're the inspector, Fred, but if you're the inspector, you want to communicate with the engineering firm to say, look, you got to make sure that if it's an Article 700 system, then you're going to want to selectively coordinate. And get them to tell you what level of coordination they're going to provide. If it's a 700, it's got to be selective coordination all occurrence all times. Get them to check that box and sign off and say that's what they're going to get you. And now that's part of record, and that's in the design engineer's mind that that's what he has to meet, and then he will approach it appropriately. If you don't get that settled up front in the because it looks like you're doing a design stage review. If you don't get that level of performance set up front, getting it after the fact is very difficult. It could cost that job a lot of money to try to fix the problems. So if you're engineering that system, then you're going to want to think of is it an Article 700, 701, or 708 system where selective coordination is required. You're going to have to meet those requirements. If it's an Article 517 system where you have 0.1 seconds, you can breathe a little sigh of relief and design as you see fit as the design engineer to achieve your level of reliability that you want to seek. 700, 701, and 708 sort of made that decision for you. So Vixar Patel, send me an email, buddy. I'll take a look at the records again. I sent those out. If you did not get a certificate for yesterday, send me a note. It could be that I just missed you. That spreadsheet was huge. I sent a lot of stuff out last night. I'll check your name. You should have my email address from all the communications going on. Oh, I had somebody who wants to start at 11 a.m. Eastern. We could do that too. We'll do some votes. I'll send out a post seminar question. You're welcome, Lewis, and you're welcome, Lon. Let's see, Monday Code. We be posting these presentations again. They're all on YouTube. Go to my site. Right, so that's all that good stuff. I'm watching YouTube. Welcome, you're welcome, you're welcome. I appreciate it. Is there a quiz for day 2 session? Jesse Garcia, you're going to want to go to menti.com and go to 842147. Menti.com, put in the code 842147. That's your quiz. Thank you. And thanks, Jeff Fecteau. Thank you very much. I appreciate the feedback, buddy. We're going to have to co-present one of these one day. Love to have you on the air, buddy. All right. We are 11 minutes after. I am going to queue up. Hey, you're welcome, Trent. Very welcome. I am going to queue up our outro, and we're going to call this session to a close. I appreciate everybody's attendance, and I appreciate everybody's attendance in this process from the 2020 code change and everybody's interest. Thank you very much for participating and providing the feedbacks through the chat sessions. I'll send a note out for the breaker basics as well. So for those of you on YouTube, you're going to get to watch an outro, and I'm playing guitar on that one. So thank you. I can also, I'm a little bit musically inclined. So take care and stay safe and healthy. So thanks a lot. Thanks for watching.